Talking about all of the different gas laws. Well, today we're going to actually take a break from those calculations and we're actually going to start talking about the kinetic molecular theory. And basically what this theory tells us is that, first of all, we have to remember what a theory is. And a theory is something that tells us why things happen. Now that's a little bit different from a law. A law tells us what happens, but theories tell us why happen. So basically it's our attempt to our best knowledge to explain why things happen the way they have. They aren't always necessarily proven, but they're a best example or explanation that we have to explain why things happen. This theory in particular explains why ideal gases behave the way they do. So in order to talk about this, we have to think about 4 different things. First of all, particles, especially gas particles, are always in constant motion. The more collisions you have of these particles, the more pressure you're going to have. So if the particles are moving faster, they are going to be colliding more often, which causes an increase in pressure. Third, we also have to keep in mind that particles exert no attractive force or repulsive forces on one another. And in the last one, the average kinetic theory of the particles is proportional to the Kelvin temperature. So basically, if we are trying to figure out the amount of energy, if the temperature is going up, the kinetic energy is also probably going up as well. Alright, so now we need to talk about what in the world does it tell us. So first of all, it helps us to describe temperature. And in order to describe temperature, we're going to use a little bit of a different type of formula. We're going to use K equals 1/2 times mass times velocity squared. And for those of you who have taken physics or physical science, you know that this is the equation for kinetic energy. So we are going to be starting off with the physics of motion because we're talking about the movement of particles. However, it's hard for us to pinpoint a particle, to measure its mass, and to find its volume. So instead of using the physics, we are going to be using the equation for the kinetic energy per mole equation. In order to find this, we take 3/2, we times it by our rate, and then again by our temperature, because rate is a constant for ideal gases, and we can easily find the temperature. So in this case, the meaning of temperature, it means that the average kinetic energy of the particles of a substance. For those of you who, looking at your note sheet, we're going to go into depth a little bit about the equation Ke per mole equals 3/2 RT, and we're going to actually talk a little bit about volume and the square and how we can rearrange equations to get to a nice equation. So if you really want to know how we get from one equation to the next, you can visit this website. If not, I'm going to show you I'm going to show you the new equation because we haven't done vectors and magnitudes in chemistry. That's more of a physics concept, so you're going to get to that one if and when you take physics. Alright, so let's do an example. So first of all, actually, let me write the equation for you. So basically, if we rearrange the kinetic energy per molecule of a particle, if we take this guy, well, the reason that velocity is squared is because we don't care what direction the particle is moving. And so if you can rearrange a few things in here, we should see that if you are going to square velocity and then you're going to take the square root of it. And what that does is it actually kind of takes out the direction. Because if you remember from physical science, velocity has a speed and a direction. Well, when we're talking about gases, we don't really care what direction they're moving in. We just care that they're moving, and we want to know how fast they're moving. We don't really care where they're going. So if you square it, that gets rid of the direction. And then if you take the square root of it, it honestly gets rid of the square, so you're left with the same thing. So honestly, what we're doing is we are taking the absolute value of our velocity. So again, go to that website if you want to see how they get from this equation to down here. But again, that's the basics of it. Alright, so now let's do that example number 1. So example number 1 says, calculate the average kinetic energy of the SO2 molecules in a sample of SO2 gas at 295 Kelvin and at 733 Kelvin. So basically, we're going to be doing this equation twice. We want to compare the kinetic energy at one temperature to the kinetic energy at the next. So let's just use the KE equation. So kinetic energy is equal to 3/2 times RR times RT. Now, up to this point, we've been using 0.0821 for RR because that was in moles and Kelvin and liters and atmospheres. However, this time we're talking about energy, so we're not going to be wanting to use that R anymore. We are instead going to be wanting to use the R of 8.314 joules, because joules is the unit for energy, per Kelvin mole. Alright, so let's just plug in our numbers. We're going to start off with the 295 Kelvin. So 3/2 times 8.314 times 295. Okay, you plug all of this in your calculator, you should get an answer of 3,680 joules per mole. Now I've already rounded that to maintain my three significant figures. So at 295 Kelvin, we're going to have 3,680 joules of energy. Because remember, this equation is technically the kinetic energy per mole. So when you're giving the answer, you don't always have to keep the mole right here in your unit. All right, so now let's look at what's going to happen when the temperature goes from 295 to 733. My guess is the energy is going to increase, but let's see if the math tells us that. So we're going to take our kinetic energy, we're going to times it by 3/2 times our R, which is 8.314, times our new temperature, which is 733 Kelvin. If you do this math, you get an answer of 9,140 joules per mole. Again, I've already rounded that number to maintain my significant figures, but what we notice is, I said I thought it would be more because 733 Kelvin is an increase in temperature. I guess that the average kinetic energy would also be an increase, and if you notice, we were right. All right, so let's look at the next part of your notes. All right, so the root mean squared, which is kind of what I was getting to in the last slide. So basically, the name of it is the root mean squared, and if you remember, we square the velocity to get rid of the negative, and then we take the square root of it to get rid of the square, and we give it a new name. And if you notice, sometimes when you see it written, you're going to see it written with a U, the Greek letter U. I'm honestly probably just going to do VRM squared so that we can remember that it's velocity, but you might see it more than one way. So let's combine those two equations. So if we combine the root mean squared that I just showed you about the velocity with our kinetic energy, we get a new equation, and we get the new equation of our root mean squared, which is our absolute value of velocity, is going to be equal to 3 times our rate times our temperature, and we see a capital M down here. Now, I don't really like the way this is written because capital M usually stands for molarity, so I'm actually going to have you guys change it to capital M for molar mass. That's what we're talking about here. So the molar mass is grams per mole. Okay, so the capital M is your molar mass, and R has, again, the same units of 8.314 joules per Kelvin mole, and the unit for our velocity is going to be in meters per second to get everything to cancel out. All right, so let's do an example with this root mean squared concept. So it says calculate the root mean square velocity of carbon dioxide at 25 degrees Celsius. So if you remember, we just talked about that. Our root mean square equation is going to be equal to the square root of 3RT divided by our molar mass. All right, so we know our R is 8.314. We need to convert that temperature to Kelvin to get our units to cancel out in our R, so it's going to be 298 Kelvin. And we're going to divide that by our molar mass. So carbon dioxide, carbon is 12.01, plus 2 oxygens, which are 16, is going to give us a molar mass of, let's see here, let me put in my calculator really quick. .44 0.01. Now, if you remember, that's grams. Well, in order to get our rate and our temperature and everything to cancel out for velocity, we need to honestly have our grams converted into kilograms, because the molar mass of this equation should be in kilograms per mole in order for everything to cancel out. So all we have to do, though, is move the decimal over 3 times. So it's going to be 0.04401 kilograms per mole. And then we, again, just have to plug this into our calculator. So this is going to give us an answer of 411 meters per second, but we can only keep 2 significant figures, so that's going to be 410 meters per second. And I know that this equation is a little bit complicated and it doesn't probably make a whole lot of sense to you right now, but we're going to do one more, and I'm honestly not going to stress it a whole lot on the test. So, alright, so let's do the next example, example 3. It says calculate the root mean square velocity of hydrogen at 25 degrees Celsius. We're going to do the exact same thing. So our velocity is going to equal the square root of 3RT divided by our molar mass, again, in kilograms per mole. So 3 times our rate of 8.314 times our temperature, which is 298, except this time our molar mass is going to be much smaller, and it is going to be 2.02 grams, but in order to convert that to kilograms, we have to move it 3 times. And now we just plug this in our calculator, and we get a really big number, and I'm going to go ahead and round it from my calculator. It's at 25 degrees Celsius, so we're going to get an answer of 1900 meters per second, which is much smaller, or much bigger. The last answer was 410 meters per second because that was a really big molecule. Carbon dioxide is much bigger than hydrogen, so it should move much slower. Hydrogen should move much faster. Alright, so the next thing we're going to talk about is this idea of effusion and diffusion. Now, I know you've heard of the word diffusion before, but effusion is probably a new one. Effusion means that the escape of gas through a tiny hole into an evacuated space. So basically, effusion is really beneficial if you have small gas particles. The smaller the particles, the easier they will effuse. Think about the doorway, okay? People can move in and out of our doorways in our school really easily because overall we're a pretty small mammal. However, if we try to put an elephant through our doorway, that's not going to work very well. So an elephant is not going to effuse through our schoolroom very well, whereas students and teachers can effuse through really well because we can fit through the doorway. Diffusion, on the other way, is a completely different concept. Diffusion is basically just talking about the spreading of a substance throughout a given volume or throughout other substances. So that's like in our classroom, if a student back here in this corner decides to spray perfume, the smell of the perfume does not just stay there. Eventually, it'll start to spread out to try to fill this entire room, but it's not going to be escaping out of the room. Diffusion is when it just is expanding through a substance. Effusion is when you are moving through tiny holes. All right, well, this idea leads us to something called Graham's law. Graham's law says that the rate of effusion is inversely proportional to the square root of the mass of its particles. So basically what Graham's law says is the less mass of the gas, or the smaller the gas, the faster it's going to move. So it gives us an equation so that we can compare our rates, which is the left, so we're talking about our speed, to our molar mass. And if you notice, the R1 and molar mass 1 are on opposite sides of the fraction, so is 2, which makes sense because they are inversely proportional. So as the speed of R goes up, the speed of our molar mass should be going down. So let's do an example problem to see what happens. Alright, so example number 4 says calculate the ratio of effusion rates of hydrogen gas and uranium hexafluoride So basically, we're going to be using that equation I just talked about. We're going to talk about rate 1 over rate 2 is equal to the square root of the molar mass 2 over the molar mass 1. Now, I'm going to kind of think one step ahead, and I think that hydrogen gas is much smaller than uranium hexafluoride, so I'm going to assume that hydrogen gas is going to be moving much faster. And since I don't like dealing with weird fractions and decimals, I'm actually going to put hydrogen gas on as 1. So 1 is going to be H2, and 2 is going to be uranium hexafluoride. So as I plug in this information, I'm going to plug them in where they belong. So the molar mass of uranium hexafluoride is 352.03 grams per mole. The molar mass of H2 is 2.02 grams per mole. And our units are going to cancel out, and if you put this in your calculator, you're going to get the square root of 174.27. Take the square root of that, and you're going to get 13.2. So if you remember, we have RH2 over RUF6, and we know something about math. We know that there's always a 1 under our fraction. So basically what this means is our hydrogen gas is moving 13.2 times faster than our uranium hexafluoride. So that's kind of how you read it. You're not solving for each individual part, but if we can get the number on the right to be over 1, you can compare the ratios relatively quickly. But let's do one more example just to make sure that we understand how to do this. Example number 5 says, how much faster is H2 than Cl2? Again, we're going to be using R1 over R2 equals the square root of our molar mass 2 over our molar mass 1. I again am going to assume that hydrogen is going to be moving faster than chlorine because it is so much smaller. So I'm going to make 1 hydrogen and 2 chlorine. And now all I have to do is plug in my molar masses. My molar mass of chlorine 2, remember our diatomic molecules, is going to be 70.9. The molar mass of hydrogen is still 2.02. So if we do a little bit of math, we get that that's 35.09. Do the square root, and we get 5.924. Now remember, it's R of our H2 over R of chlorine, and remember this is technically over 1. So what this number is telling us is that hydrogen is moving 5.924 times faster than Cl2. Okay, so what I would like for you guys to do right now for the rest of the hour is I want you to work on the kinetic molecular theory of gases example problems, and then I also want you to work on assignment number 7, which gives you a little bit of practice of doing these calculations with effusion and the concept of diffusion. If you have time and you want to, you are more than welcome to do assignment number 6 using that same PhET simulation that we used the other day in class, but that assignment is optional. You can do it if you want to. If not, you can just continue to work on some of your lab calculations from yesterday, and I will help you when I get back tomorrow.